Good afternoon, chemistry students. It's 12:37 on April 6th. I'm posting this very quick video on the exit slip 2.8 about catalysts. Okay, so just a little heads up. I'd love to have the time to give everyone all this awesome positive feedback, but it's very time consuming to deliver comments on Google Classroom for almost 50 of you. So if there's nothing down on your exit slip, it means it's good job. It means it's totally right. If there's a mistake, I will make a comment on it. Sometimes if there's like a small specific mistake, I'll write a more elaborate response. But if I see that a lot of people are making the same mistake, I'll make a video like this. And there is something that I wanted to talk about that I think is really important, a big misunderstanding as well as some sort of confusion. And it centers around question number 76. So I will very quickly go over this. I will post this video and you can check this out along with the work that you submitted last Friday. All right, so first of all, this is a really important question. It's very common to the kind of question you'll see on the Regents exam. They give you a passage, they give you a chemical equation, and then they give you 3 questions. 76 and 77 both relate to kinetics, but 78 is a review to the moles unit. So they're all within this one cluster of questions, but they cover different topics. So I thought it was a really good question for you guys to see and to practice. The biggest thing that I wanted to go over is number 76. It says, on the labeled axis in your answer booklet, draw a potential energy diagram for the reaction represented by this equation. And had you had a separate answer booklet, or if you were taking the Regents exam, it would be a simple axis like this. And they would ask you to doodle an endo or an exothermic reaction. So they want you to draw a potential energy diagram for this reaction. Well, I asked you down here, since you couldn't draw it, I told you to tell me whether this was endo or exothermic and how you know. So what we'll do is we'll answer my question, then I'll come back and I'll doodle what it should be over here. And in the process of answering my question, I will clarify a big misunderstanding. So first of all, it's a simple equation. It's CO plus O2 turning into CO2 plus heat. So you have carbon monoxide plus oxygen turning into carbon dioxide plus heat. That's your equation. Is this endo or exothermic? That's the question. Well, heat is a product. And when heat is a product, it's exothermic. And I had a lot of people make a mistake on that. Now, I'll go over what they said. So it's exothermic. Okay? Now, if you want to go doodle what that should look like, there you go. So it's exothermic. Okay? Exothermic reactions should start up high and they lose energy. They go down. Sorry about that little hitch in the graph there. Okay, I'll erase that. So exothermic reactions, the potential energy of the reactants is higher than the potential energy of the products. So if you actually were to solve this, there we go, that's better. So that's what an exothermic reaction graph would look like, with time being your x-axis, or it's called the reaction coordinate, and then you have potential energy here. Okay, so that's the answer. It was exothermic, and that leads me to the big misunderstanding that I think a lot of you guys have. I'm going to scroll down here and show you. There are 3 ways you could see exothermic reactions written. I just arbitrarily chose the formation of ammonia, okay, for the reaction. So exothermic reactions can be written 3 ways, as well as endothermic reactions. Exothermic reactions can have a specific amount of heat be on the product side. They could have a general word. It could say heat. Like maybe they don't specify how much heat it is, but instead they just say heat. In both of these, you see that heat is a product. When they include heat, whether it's a specific number of heat in kilojoules or the general heat, just the word heat, when they include it as a product, it's always exothermic. Okay? When they don't include it into the equation and they put it off to the side like this, in parentheses, with the delta H there, when they do that and that delta H is negative, it's also exothermic. Okay? So if you were reading this one down here on a test, you could actually draw it like this and have it mean the same thing. Okay? So that's exothermic. On the other hand, what's that? Phone's buzzing. Sorry about that, guys. Such is life here. The endothermic reaction is the opposite. You'll notice in the first two ways, when they include the heat into the equation, whether it's the actual specific amount of kilojoules or just the word heat, when they include it into the equation, endothermic will be the heat will be a reactant. So notice that you have your heat here or here. That tells you it's endothermic. Whereas in exothermic, it's a product, which was here and here. Okay? So the last way you could see it, sometimes they'll, like again, when they don't include it into the equation and they put it off to the side in your parentheses, if the delta H is positive, you know that it's also endothermic. And if you wanted to take this format down here and make it into this one, all you'd have to do is put in the 150 kilojoules in the reactant side of the equation and you're done. One thing that I noticed is that a lot of students were saying on the exit slip, oh, well, according to the equation, the delta H is positive. Therefore, it's endothermic. And I totally understand the misunderstanding there. But notice down here, when the delta H is positive, it's endothermic. Okay, the way we do it when we actually put the heat in the equation, when the heat is over here as a product, we say it's being released. Okay. When heat is a product, we say it's being released and it's exothermic and the delta H will be negative. All those things are true for exothermic reactions. On the other hand, when we keep the heat as a reactant, we say it's being absorbed. Okay? We say that heat is being absorbed and that the delta H is positive and therefore it's endothermic. And the last thing I can do for you guys to help you try to understand this is to draw the actual PE diagrams. In this case, for an endothermic reaction, the potential energy starts here and it ends with more potential energy. So you absorbed this much energy. That's your delta H, and you know that it's positive. You have a big number minus a small number, you're going to get a positive delta H. Okay? On the other hand, in this case, exothermic, going back to our sketch, you start higher and you end with lower amounts of potential energy. You are releasing that energy. Okay, you're releasing that much energy, and therefore you have a small number because the products minus the reactants. You have a smaller number minus a bigger number. You're going to get a negative delta H. Okay, so don't be confused by that. When you see they write the heat, either the numerical form of the heat or they just write the word heat, when they include the heat in the equation, if it's a product, it's exothermic, the heat is released, and the delta H is negative. When they include the heat in the equation and it's a reactant, okay, we're going to consider that endothermic. Heat is being absorbed and the delta H is positive. Okay, all right, so that was the major misunderstanding that I saw. Go back to your exit slip here. See if it lets me go over those last two. All right, and number 77, compare the activation energy of the catalyzed reaction to the activation energy of the uncatalyzed reaction. Just got to know your definition of catalysts. Okay, they increase the rate of reaction by lowering the activation energy. So let's say there's my uncatalyzed reaction without a catalyst. And if I did it in green, I'll do it in blue for the catalyzed reaction. You start at the same place, but you take a pathway with a lower activation energy and you end at the same place. So the activation energy of the catalyzed reaction is going to be lower than the activation energy of the uncatalyzed reaction. That was the answer I was looking for there. Okay. Notice the activation energies are lower when you add a catalyst. And number 78, I'm going to go through this kind of quick, but your mole ratio, it's asking for CO and O2. So going back to this is something we did in class. So we're talking about O2 and CO. The mole ratio is 2 to 1, right? It's a 2 to 1 mole ratio. So for every 2 moles of CO you're going to need half as many moles. Excuse me, for every 2 moles of CO you're going to have 1 mole of O2. So what happens if you have 28 moles of CO? So your mole ratio, you have 2 moles of CO. For every 1 mole of O2, you have to make your mole ratio. Okay, so there's your mole ratio. And now ask yourself, draw my line, if I have moles of CO on the top, I need moles of CO on the top on the second fraction as well. So I'm going to write moles of CO. And I know I need moles of O2 on the bottom. Last but not least, you're going to go to the equation and figure out which of those will get a number and which of those will get X. Determine the number of moles of O2. So we want to know how many moles of O2. That's X moles of O2 will completely react with 28 moles of CO. So CO is going to have the 28. So this is what you're solving. 2 over 1 equals 28 over X. You're going to cross multiply, solve for X. You're going to get 2 times X is 2X. 1 times 28 is 28. You divide both sides by 2, and you should have gotten your answer, which would be 14 moles. Sorry, I'm going to do this in red. 14, I'll do it right. I'll keep it consistent for you guys. You're going to get 14 moles of O2 should have been your correct answer. Okay? So hopefully that helps. You guys can go over that. If you got them all right, great job. If you got them all right, but you didn't quite know, you can double check your work. If you were totally lost, I hope this video helped you guys. All right, that's it, guys. Have a great day.